Hi, welcome to Orozco's Lectures. I am Jose Orozco, and these are my lectures. This lecture is a Calculus 1 lecture. I hope you enjoy it. This is chapter 5, and chapter 5 in general is about what integration is. Alright, specifically 5.1. Well, before we talk about integration as a whole, we're going to talk about antiderivatives and indefinite integrals. Alright, so let's start first with a definition here. Alright, we're going to start with what an antiderivative is. A function f. Notice I'm using capital F. Alright. I will be using capital F and lowercase f to talk about slightly different things there. Alright. They will be related, but we'll see how. A function capital F is an antiderivative of lowercase f on an interval I when capital F prime of x is equal to lowercase f of x for all x in I in our interval, right? So, and here what we're saying is this function f is an antiderivative of this other function f, right? So this function capital F is an antiderivative of this lowercase function f, lowercase f, if the derivative of this big one is the same as just this one, as it is, all right? And I want to make a distinction here. Notice I said an antiderivative, all right? So let's talk about that little statement there because it implies something. So it's an antiderivative, not the antiderivative. And I want to make the distinction now because what we're saying here is that antiderivatives are not unique. Antiderivatives are not unique. So what do we mean by that? So take, for example, to consider this function f of x is equal to x cubed, and also this other function g of x is equal to x cubed, what's a cube? X cubed plus 2. All right. And if I take the derivatives of these, well, what do I get? Well, capital F prime of x would be 3x squared. Capital G prime of x would be 3x squared, right? Because the derivative of a constant is 0. So notice here that they both have the same derivative, but they're clearly not the same function. They're similar, right? But they're not the same function. So what I'm getting at here is that f of x is not equal to g of x, but f prime of x is equal to g prime of x. So if I started with 3x squared and I said, well, what's the antiderivative? Well, we've got two different options. In fact, we have infinitely many options, right? Because we can say that in here, let's look at, for example, here, if I call h of x, if I just call it simply x cubed, well, we can have plus 1, plus 2, plus 3, right? By that I mean x cubed plus 1, x cubed plus 2, x cubed plus 3, or minus 1, minus 2, minus 3. And every single one of these would have the same exact derivative because the derivative of a constant is 0, right? Now, how do we account for that, right? That's what we mean when we say an antiderivative, because there's a lot of multiple options here. So how do we account for that? The way that we account for that is we essentially say, well, the antiderivative. So the antiderivative of this case in here of, let's say, 3x squared, we're going to say it is, well, for both of these, they came from an x cubed, right? So we're going to say it's x cubed plus c plus some constant, all right? That c there is called the constant of integration, all right? This is the constant of integration. We'll talk about that a little more later too. But again, this represents in here, for the antiderivative of this function, we had all these options. This c represents all of those possible constants there, all right? Now, so let's look at an example. Let's say that we have that a function that said the derivative is 7. So dy dx is 7. And the question is to solve this differential equation. All right, so solve the differential equation. And what we mean by that is find y, solve for y. Right? And in here, well, we're saying the derivative of some function is 7. Well, that's how we solve it. Well, what is y? What is the function whose derivative is just 7? Well, using the constant rule, that looks like 7x, right? Because if I start with 7x, its derivative is just 7. And, well, you know that we can just add a plus 1, and its derivative is still 7. If we can add a plus 2, its derivative is still 7, right? So this is, again, why we just say it's going to be 7x plus c, right? Because we have infinitely many options there as to what that c could be. Before we do more examples, I want to make a note here. So when solving a differential equation, it is convenient to use the following form. To use the form dy dx is equal to f of x. All right. And I should be saying dy dx is equal to f prime of x. All right. Because the derivative of the function is that f prime. And we can use the idea of differentials, right, to rewrite this as dy is equal to f prime dx. All right. So we can write it in differential form. All right. It is very convenient to do so. Now, so let's see why. Well, before that, let's write a definition. The process of finding the antiderivative is called antidifferentiation. Which is very, very clever, right? Because the process of finding the derivative is differentiation. So that's that. It's also called in finding the indefinite integral or indefinite integration. All right. We denote it using the following symbol. Right. All right. That's the integral sign. All right. So in general, what we can say is that if I had the integral of dy, this would be the integral of, let's use lowercase f dx, right? If I start with that, well, then here y would be, well, the integral of lowercase f of x dx will be capital F of x, and then we'll do plus c. In general, we don't really write this integral of dy that way, at least not at this level. in general, we'll be using y equals the integral of f of x dx is equal to capital F of x plus c. All right. And again, in here, well, let's talk about what each piece here is. All right. And perhaps I'll redraw it over here. Or maybe I'll just shift it. There we go. So each piece here has a name. All right. So let's talk about what it is. This is the integral sign. It's important to know these names so that you know what I'm talking about whenever I reference them throughout the thing. This f of x here, that's our integrand. All right. This right here, this tells us the variable of integration. And here, this is an antiderivative of f. That's just antiderivative. Let's try writing that again. Antiderivative. This c is our constant of integration. And overall, what we have, ooh, that's not what I meant to do. What happened there? This whole thing, f of x plus c, that's when we start using the term the integral. Or the antiderivative, excuse me. Versus an antiderivative. Right, because here we're just talking about the generic antiderivative. Okay, so now, how do we pronounce that? So how is this pronounced? So this is the integral of f of x with respect to x. Or the antiderivative. Either way works. Antiderivative of x with respect to x. And here also I said the integral. We'll talk about why that's why we're able to say that. But now, basic integration rules. And well, what do we mean here? When we say the antiderivative of f prime of x dx, well, that would just be, so notice I use capital F prime, that would just be capital F of x plus c. If I take the derivative with respect to x of the integral of f of x dx, that is equal to f of x. So what we're saying here is that taking the derivative and the antiderivative are inverse operations. So the integral of a derivative is the function. The derivative of the integral is the function. All right. So now, let's write down what some of these rules are, and there's quite a few. All right. So if I take, well, I'm going to compare the differentiation rules with the integration rules that go with it. So differentiation rules, and then over here I'll do the integration rules. Right, because they're very much associated with each other. So if I take the derivative with respect to x of a constant, that's 0. Well, similarly, the antiderivative of 0 with respect to x is just a constant. The derivative with respect to x of some letter times x is just that letter, right? So that letter meaning some number, right? Some number k times x, the derivative of that is just that constant k. The integral of a constant is a constant times x plus c. We know the derivative of a constant times a function is that constant times the derivative of the function. Similarly here, the integral of k times f of x dx would be the same thing as saying k times the antiderivative of f of x dx, right? I guess we can write this as k times capital F of x plus c, where capital F of x represents the antiderivative of lowercase f of x. We know the derivative of the sum and difference of two functions. We could just say that's f prime of x plus or minus g prime of x. Well, similarly, that applies over here. If I have the antiderivative of f of x plus or minus g of x dx, well, I would end up with capital F of x plus or minus capital G of x plus c, right? Essentially, I can split up the integral. Perhaps I should have done that in the second line. All right, here we go. Right, so here I'm saying this. Right, so we can essentially distribute this integral sign. All right, just like over here, we can distribute the differentiation. All right. So now let's look at some actual examples or some more rules. The derivative with respect to x of x to the n. Well, we know that that's a power rule, right? So that's n times x to the n minus 1. Well, what was the process here? We brought the exponent down to the front, so we're multiplying by the exponent, and then we subtracted 1 from the exponent. Well, if we want to find the antiderivative of x to the n dx, well, what would be the exact opposite of this, right? Because they're inverse functions, so we need to do the exact opposite. Well, instead of subtracting 1, we're going to add 1 to the exponent. And instead of multiplying by that exponent, we're going to divide by the new exponent. All right. So essentially here, we need to do everything in reverse, right? So brought this to the front, so multiply it by original exponent, subtract by the exponent. Well, do the exact opposite. Add 1 to the exponent, opposite multiplication, divide by the new exponent. All right. And then plus c. We know the derivative of sine is cosine. So then the antiderivative of cosine is sine plus c. We also know that the derivative of cosine is sine, not sine, negative sine. Well, the antiderivative of sine would be negative cosine. All right. And in here, before we continue, I want you to keep something in mind whenever you think about the sine and cosine when it comes to derivatives and antiderivatives. You can make this way, right? And in a previous lecture, I mentioned that going this way, it was derivatives, right? The derivative of sine is cosine, the derivative of cosine negative sine, the derivative of negative sine is negative cosine, the derivative of negative cosine is sine. So going this way is derivatives. Going the other way, going counterclockwise, that's antiderivatives. So the antiderivative of sine, negative cosine, the antiderivative of negative cosine, negative sine, the antiderivative of negative sine, cosine, the antiderivative of cosine, sine. All right. So this is a good little chart to keep in mind whenever you're working with sine and cosine in order to remember that pattern. All right, so now, so we did sine, cosine, so let's look at the derivative of tangent. We know that the derivative of tangent is secant squared. Well, that tells me the antiderivative of secant squared is tangent plus c. We know the derivative of secant is, well, the derivative of secant is secant x tan x. Well, that would tell me the antiderivative of secant x tan x is secant. We know the derivative of cotangent to be negative cosecant squared. Well, that would tell us the antiderivative of cosecant squared would be negative cotangent. If I did the derivative of cosecant, well, that's negative cosecant cotangent. So it would tell me the antiderivative of cosecant cotangent is negative cosecant x plus c. We know the derivative of e to the x is e to the x. So the antiderivative of e to the x dx is e to the x plus c. Right? The derivative of a to the x was a to the x times ln of a. The antiderivative of a to the x is going to be a to the x divided by ln of a. The derivative of ln of x, that's 1 over x, and that's for x being greater than 0, right, for the domain here. The antiderivative of 1 over x is ln of the absolute value of x plus c. And we take the absolute value there because, well, technically, for 1 over x, we could plug in negative values, right? So the domain for 1 over x is different than for ln. So we want to make sure that when we go to ln, we are okay in the domain, all right? We know that the derivative, well, actually, we'll leave it as that. Now, let's do actually some examples, all right? So find the antiderivative. Now we're going to do a bunch of examples. So we already did one example. So example B. Let's say the antiderivative of 4x dx. Well, in here, we can, if we really use all the rules that I wrote above, we can rewrite this as 4 antiderivative of x dx. And from that one rule for the power rule that I started with there, we add 1 to the exponent, divide by the new exponent. So we have 4 times x to the 1 plus 1 divided by 1 plus 1, right? And then plus c. So what is that? Well, 1 plus 1 is 2. So I have 4x squared over 2. That's 2 plus c. Can't forget the plus c. And that equals now 2x squared plus c. All right. So technically, those are all the steps in between there. All right. Do you have to do all the steps there? No. You can go straight from here to here. Well, I normally go from here to here just so that I don't reduce things in my head and then go forward. All right. C. So if I had the integral of 1 over x to the fifth dx, notice that I can write this as the integral of x to the negative 5 dx. And then what happens when I add 1 to that exponent? I get negative 4 divided by the new exponent, negative 4 down here, and then plus c. So we can really write this as negative 1 over 4x to the fourth plus c. If I have the integral of, let's do x to the 1/2. Well, add 1 to the exponent, 3/2, divide by the new exponent, plus c. But we know that when we divide by a fraction, it's the same as multiplying by the reciprocal, so we can really write this as 2x to the 3/2 over 3 plus c. If I have the integral of 9 cosine of x, then that would be 9 sine of x plus c. If I have the integral of 7 over x, well, that would be the integral of 7x to the negative 1. Right? And then we would say, well, add 1 to the exponent, divide by the new exponent. And we still have that 7 in the front. That's bad, because we're dividing by 0. So that's not really how we want to do this one. Right? That was fine when we had the x to the fifth on the bottom, but now when we just have x on the bottom. So what do? We had a definition for that. Where is it? There it is. The integral of 1 over x dx. All right, so that's just ln of x. All right, so let's see how that applies. So in here, what we're going to say instead is we're going to say this is just 7 times the integral of 1 over x dx, and that would give us 7 ln of x plus c. So make sure that if you have just x to the negative 1, you don't do this. You don't add 1 to the exponent. It's ln. All right. So g. The integral of just dx. Well, this is really saying the integral of 1 dx, and the integral of 1 would just be x plus c. The antiderivative of 4x minus 7. Well, technically, this is the antiderivative of 4x dx minus 7 times the antiderivative of dx. But what we can say here is this one right here we already did, right? Add 1 to the exponent divided by 2, I ended up with 2x squared dx, right? So just 2x squared plus c technically. But minus the integral of 7 dx is just 7x, and then we do the plus c at the end, right? Normally, I don't actually write that middle step. Normally, I just go straight from here to there, all right? All right, so let's say I have the antiderivative of 5x squared minus 7x squared, 5x to the fourth. That's a 4. 5x to the fourth minus 7x squared plus 3x minus 8 dx. Well, what would that be? Well, this first one. Add 1 to the exponent, divide by the new exponent. So x to the fifth, and divide by the new exponent, right? That 5 is still there. Add 1 to the exponent, divide by the new exponent. Minus 7. Add 1 to the exponent, divide by the new exponent. 3. Add 1 to the exponent, divide by the new exponent. Minus, now we have the antiderivative of a constant. So minus 8x, and then plus c. And here these 5's cancel out, right? So we end up with just x to the fifth. But the rest of those don't reduce. All right. J. Let's say that we have the antiderivative of x plus 6 over the square root of x dx. Well, I can really write this as the antiderivative of x over radical x plus 6 over radical x, right? And at that point, well, x over radical x, that's just saying x over x to the 1/2. subtract the exponents, and then with 1/2. This one over here, I can write it as 6 to the negative 1/2, right? And then what does that give me? Well, that gives me now add 1 to the exponent, x to the 3/2 divided by the new exponent, but dividing by a fraction is the same as multiplying by the reciprocal, plus 6, and then add 1 to the exponent, multiply by the reciprocal, right? Divide by the fraction. So really this gives me 2x to the 3/2 over 3 plus 12x to the 1/2 plus c. Let's say I had the integral of, or the antiderivative of cosine of x over sine squared of x. Well, in here we can rewrite this as cosine over sine times 1 over sine. And then cosine over sine is cotangent, so we have cotangent times 1 over sine is cosecant. And the antiderivative of that, well, we have cotangent times cosecant. That's the same as cosecant times cotangent. The antiderivative of that is negative cosecant. Plus c. Oh. Let's say that I have x plus 1 times 3x minus 2 dx. All right. Before I do that, I'm going to make a note here. The integral of f times g is not the integral of f times the integral of g. All right. That is not a thing. All right. So don't think that we can just take the integral of this piece and then the integral of that piece, and then that will be our answer. No. What we need to do here is distribute this inside. So x times 3x squared, the x times 3x is 3x squared, negative 2x, plus 3x minus 2, right? All I did there was FOIL, reducing, in other words, combining like terms, right? Those two are x's, so we have 3x squared plus x minus 2 dx, giving us, well, the antiderivative of this. Add 1 by, so we have 3, add 1 to the exponent, divide by the new exponent, add 1 to the exponent, divide by the new exponent, the negative 2x, finally plus c. Those 3's reduce, so our answer is x cubed plus x squared over 2 minus 2x plus c. M. Let's say that I had the antiderivative of theta squared plus secant squared of theta, d theta. Notice here that, well, this is different, but only because I'm using theta as our variable. In general, the process is the same. Add 1 to the exponent, so what do I get here? I get theta cubed. Add 1 to the exponent, divide by the new exponent, plus the antiderivative of secant squared was tangent, plus c. Let's say that I had the antiderivative of t to the 4th minus 3t squared plus 5 over, let's do t to the 4th. Let's do t to the 3rd dt. All right. So what does this give us? This gives us, well, what we want to do here is just apply rules of fractions. So what I have here, and notice here I'm using the variable t, but again, because I'm integrating with respect to t, that's fine. It's just a new variable. So what do I end up with? Well, I'm going to rewrite this as t to the 4th over t cubed minus 3t squared over t cubed plus 5 over t cubed dt. But then t to the 4th over t cubed is just t. T squared over t to the 3rd is t on bottom. And then 5 over t to the third can just be rewritten as 5t to the negative third dt. And now to find the antiderivative here, add 1 to the exponent, divide by the new exponent, minus 3 over t. Remember, that was a very specific one, right? When we have our exponent being negative 1, it's just ln of the absolute value of that variable. And this one will add 1 to the exponent, divide by the new exponent, plus c. I'm just going to go ahead and rewrite this as t squared over 2 minus 3 ln of t, well, absolute value of t. It's important to have the absolute value. And then minus 5 over 2t squared plus c. So that's n. M. Let's say that I have the integral, or the antiderivative, excuse me, of secant of y times tangent of y minus secant of y dy. So what would that be? Distribute that secant. So I have secant of y tan y minus secant times secant is secant squared dy. And then the antiderivative of secant times tangent is just secant. The antiderivative of secant squared is just tangent. And then plus our constant of integration c. All right. And if I had the antiderivative of 3 to the x minus 5 over x dx. Well, an antiderivative of that would be 3 to the x over ln of 3 minus 5 ln of x plus c. Right? Yeah, we'll just leave it at that. So now, those were all just finding antiderivatives, right, of a whole bunch of different scenarios. Let's talk about something called initial value problems. Right? Initial value problems. Sometimes these are also called initial condition, right, problems. Right, but it's the same exact thing, the initial condition or initial value. So we know that if I have y being equal to an antiderivative of f of x dx, this had infinitely many solutions, right? We said this game became capital f of x plus c. So we know there's infinitely many solutions. Infinitely many solutions. But for example, if I had y equals, so if I had this antiderivative of 3x squared minus 1 dx, right? This became x cubed minus x plus c, right? Now, that function, x cubed minus x plus c, what does that look like? If I just look strictly at x cubed minus x, right? So here in yellow, I'm going to look at x cubed minus x, right? So that function. Let's do it this way. So that would look something like this. Right? But because of that plus c, we have many possible versions of that, right? Because that plus c just represents a vertical shift. So in here, that plus c represents all of these blue ones that I'm drawing, right? And obviously there's infinitely many ones, infinitely many different of those blue copies, right? Just shifting it up and shifting it down. But let's say that I wanted a specific one. What if I was interested in this one? How do I get that specific one? Well, that's what this initial value problems do. It allows us to look for a very specific one that would give us the function that we were looking for. So, for example, so let's go ahead and do an example. So, well, what letter was I at? N. So O. So let's say let this function f of x be equal to the integral of 3x squared minus 1 dx. And let's say that I already know that f of 2 is equal to 4. All right. So this right here, that's what we're calling our initial condition or our initial value. All right, initial value or condition. So let's see. Well, we know what f of x is. We already calculated that antiderivative, right? It was x cubed minus x plus c. But we also know that when I plug in 2, I'm supposed to get 4. That's what this is telling me, right? This initial value, this initial condition, is telling me that when you plug in 2 into x, you get 4 for what? For y. So in here, well, f of 2 would normally be 2 cubed minus 2 plus c, and we're saying that has to equal 4. So now this allows me to solve for a specific value of c here. All right, so 2 cubed is 8. 8 minus 2 plus c. 8 minus 2 is equal to 6. So if I add 6 to both sides, I end up with 10, right? So what we're saying here is that the actual function that I want is actually x cubed minus x. Hold on, I added 6. I should have subtracted, right? I should have subtracted. Look at that. Negative 2. There we go. Because 4 minus 6 is negative 2, right? This together is 6, so to get rid of it, subtract. All right, so minus 2. There we go. So that's the function that we're interested in, right? And we can verify that by plugging in the 2, right? 2 cubed, 8. 8 minus 2, 6. 6 minus 2, 4. Good. So that's the actual, that's what these initial value conditions are about. So let's do a couple of more. So that was O, okay? So P. Let's say that I said that f prime of x is equal to 10x minus 12x cubed, and I know that f of x, this means that f of 3 is equal to 2. So this right here is my initial value. This right here is saying, well, I've got f prime of that being that. So what is the function f? Well, we know that f of x would be the antiderivative of f prime of x dx, which in this case means the antiderivative of 10x minus 12x cubed dx. And what does that give us? Well, we still have that 10. Add 1 to the exponent, divide by the new exponent. Minus 12 times x, add 1 to the exponent, divide by the new exponent, and then that plus c. We can reduce that to say that that is 5x squared minus 3x to the fourth plus c, right? That's our function f of x in general. But we have this initial value. We know that when we plug in 3, we're supposed to get 2. So that allows us to figure out what the value of c is for this case. So here we have 5 times 3 squared minus 3 times 3 to the fourth plus c. That's supposed to give us 2. All right, so what does that give us? 3 squared, 9. 9 times 5, 45. Minus 3 to the fourth, 81. 81 times 3 is 243 plus c equals 2. So in here, well, if I subtract 45 from both sides, I end up with negative 243 plus c is equal to negative 43. Subtract that negative 43, excuse me, add, right? I need to add now. Add the 243 to both sides, I end up with c is equal to 200, right? So what that tells me now is that the function that I was really interested on was, the solution here is 5x squared minus 3x to the fourth plus 200. All right. Next one. So that was P, Q. Let's say that I had that f prime of x was e to the x, but that f of 0 is equal to 9. Well, we know that f of x is the antiderivative of f prime of x, which gives us the antiderivative of e to the x dx, which gives us e to the x plus c. But I know that when I plug in 0, I'm supposed to get 9. So that means f of 0 is e to the 0 plus c, and I'm supposed to get 9 out of that. E to the 0 is 1, so 1 plus c is 9, telling us that c is equal to 8, right? Subtract 1 from both sides. So now that I've got that value of c, that tells us that f of x is actually equal to e to the x plus 8. So R. Let's say that I had the following. F double prime of x is equal to x squared. F prime of x is equal to, f prime of 0. F prime of 0 is equal to 1. And f of 0 is equal to 4, right? So in here, notice that I have two initial conditions given this f double prime of x. Well, let's see what we can do here. Well, we know that f prime of x will be the antiderivative of f double prime of x, which means I have the antiderivative of x squared dx, giving me x cubed over 3 plus c, right? I want to the exponent divided by the new exponent. Now, I know that if I plug in 0, I'm supposed to get 1. So that's going to allow me to solve for this c. So f prime of 0 would be 0 cubed over 3 plus c, and that's supposed to be 1. So c is equal to 1, right? 0 cubed is 0, divided by 3 is still 0. So now I've got that f prime of x is equal to x cubed over 3 plus 1. Now, f of x. F of x would be the antiderivative of f prime of x dx, which would be the antiderivative of x cubed over 3 plus 1 dx. And what happens when we do that? Well, the antiderivative there, add 1 to the exponent, divide by the new exponent. Well, so I already have a 3 down there, so it really becomes a 12 on the bottom, right? Plus the antiderivative of 1 is x, and then that plus c. And at that point, well, what happens? We get that we know that f of 0 was supposed to be 4, right? That was our other condition over here. So when we plug in 0, I have 0 to the 4th over 12 plus 0 plus c equals 4. Therefore, c is equal to 4. So that tells me then that f of x is actually x to the 4th over 12 plus x plus 4. All right. So that was R. S. Let's say that I have f double prime of x being equal to sine of x, and I'm given that f prime of 0 is equal to 1, and f of 0 is equal to 6. All right, so let's see what that gives us. And again, this was f prime. So we know that f prime of x is the antiderivative of f double prime of x, which gives us the antiderivative of sine of x dx, and the antiderivative of sine is negative cosine plus c. But we know that when we plug in 0, we're supposed to get 1. So f prime of 0 will be negative cosine of 0 plus c, and that's supposed to give me 1. So in here, negative cosine of 0. Well, cosine of 0 is negative 1, so I have negative negative 1 plus c equals 1, which tells me that c is equal to 2. And I did some bad arithmetic there, but mostly because I messed up right here. Cosine of 0 is just 1. Cosine of 0 is just 1. The rest of this is fine now, right? Because I get negative 1 plus c is equal to 1. Add 1 to both sides. All right. So now that tells us that f prime of x was negative cosine of x plus 2, right? And now, well, to solve for f of x, we got to take the antiderivative of f prime of x. So that means the antiderivative of negative cosine of x plus 2 dx. And the antiderivative of negative cosine, well, the antiderivative of cosine is sine, so I end up with the negative of sine of x, which is just really saying negative sine x, right? And then the antiderivative of 2 is 2x, and then that plus c. But we know that when we plug in 0, we were supposed to get 6, right? So this tells us negative sine of 0 plus 2 times 0 plus c is equal to 6. Sine of 0 is 0, so I have 0 plus 2 times 0 is 0 plus c is equal to 6, so c is equal to 6. Giving us now that our actual value, our actual function f of x is negative sine of x plus 2x plus 6. All right. All right. Now let's do a word problem. And what was I at? S? Yeah. So t. So a ball is thrown vertically upward from a height of 6 feet with an initial velocity of 60 feet per second. And we're going to ask 2 questions here. The first question is find the position function s of t. All right. And the second question that we ask here is what is the max height, the maximum height of the ball? All right. So first, to answer the first question, find the position function s of t. Well, let's see what we have here in this scenario. We've got a ball that's thrown vertically upward, right, directly upwards, and we know that it was thrown from a height of 6 feet. So what does that tell us? That tells us that the initial height, the initial position, so with the position at time 0, is 6. What else does this tell us? Let's see. With the initial velocity of 60 feet per second, that tells us that initial velocity, so v of 0, is 60. Recall that velocity is the derivative of the position function. So we're saying s prime of 0 is equal to 60. And we need to find the position function s of t. So in here, how do we do this? Well, what's affecting the ball at all times, right? Well, the ball's being thrown up and down. What's affecting the ball? And what's affecting the ball is the gravity. Gravity is the acceleration, right? So I know that acceleration in general is we're using feet, right? So it's negative 2 feet per second squared. This was feet per second, and this was feet. Okay. So we know that the acceleration is negative 32 feet per second squared. So what that tells us now, well, recall that acceleration is just the derivative of velocity. And we already know that velocity is just the derivative of position. So this is telling us that s double prime of t equals v prime of t equals a of t, right? So we've got now enough information to figure out what the position function s of t is. So we're going to start by saying, well, s prime of t would be the antiderivative of s double prime of t, dt. In this case, well, s double prime of t is just our acceleration function, so it's the antiderivative of negative 32 dt, giving us negative 32t plus t. Right? So now that we did that, well, that gives us negative, so that's s prime of t is equal to negative 32t plus t. So we can use now our initial value condition over here that the initial velocity, in other words, s prime of 0, is 60. So I get negative 32 times 0 plus 60. Excuse me, plus c, sorry. Plus c equals 60, which tells me that c must be 60. So that s prime of t is negative 32t plus 60. At that point, I can figure out my position function s of t by saying it's the antiderivative of s prime of t dt, which ends up being, well, the antiderivative of negative 32t plus 60. So add 1 to the exponent, divide by the new exponent. Add 1 to the exponent, well, just becomes t to the 1, and then plus c, right? So really that tells us that s of t is really negative 16t squared plus 60t plus c, right? And what were we given? We were given the initial height then to be 6 feet, right? That's where the ball was thrown from that height. So s of 0, which is negative 16 times 0 squared plus 60 times 0 plus c, well, that's supposed to be equal to 6. So that c then is equal to just 6, right? Because that's 0 and that's 0. So that gives me now the position function to be negative 16t squared plus 60t plus 6. So that answers the first question. The second question was, what is the maximum height? What is the maximum height? Well, let's think about what this scenario looks like, right? If this thrown, well, what do we have? We had from a height of 6 feet, right? So this is 6 feet. Some ball was thrown directly upwards, and then it falls downwards, right? Over time, what does that look like? So if I had this graph here of height over time, well, what does that look like? Well, at the very first position is here. Well, actually, let's do it this way. Let's say that when time is equal to 0, when it's first thrown, it is here. A second later or a moment later, it will be up here. Moment later, right? Because it's going upwards in height, right? And then at some point it starts going downwards over time. Over time, this ends up looking like this, right? And that shape should look familiar because it's a parabola, and that should make sense, right? Because we have a downward facing parabola, negative squared, so a negative quadratic function here is a downward facing parabola. So how do I find the maximum height? Well, the maximum height is where we have a tangent line of slope 0. And when does that happen? Well, it happens at the critical values, right? And how do we find the critical values? We take the derivative. So for part 2, we had that s of t was negative 16t squared plus 60t plus 6. Well, if I want to find that value there, what I need to find is s prime of t, which we already know what it was. It's negative 32t plus 60, right? This 6, it goes away because I'm taking the derivative. And at that point, well, what do? We have to set this equal to 0, solve for t. So t is negative 60 over 30 over negative 32. Negative over negative is positive, 60 over 32. Well, they're both divisible by 4, so 60 divided by 4 is 15. 32 divided by 4 is 8. Right, and I already said negative over negative is a positive value. So this tells us that this happens when t is equal to 15/8. All right, that's the maximum value. That's the maximum height. So what do we do then? So now to answer the original question is what is the maximum height? Well, we gotta plug in that 15/8 into our precision function. So that gives us negative 16 times 15/8 squared plus 60 times 15/8, and then that plus 6. All right. I'm not gonna do the entire calculation here, but you should check this yourself. That it becomes 249 over 4, which becomes 62.25 feet. All right. I'll let you figure out the calculations in the middle, but you should verify that that's the answer that you get. All right, so that is the end of 5.1. Wasn't that fun? If you think I made a mistake somewhere, you're probably right. Tell me all about it in the comments. If you feel you learned something from me in this video, hit the like button, hit the subscribe button, but more importantly, share it. Share this video with your classmates. And remember, you don't have to like math in order to be good at it. But you do have to be good at it. I am Jose Orozco. Goodbye.